Hi everyone, welcome back to TD2. In our last lesson, we learned what logistic regression was. We cleaned our data set, encoded the categorical variables, and we made sure that all of our data types were numeric so that the model could process them correctly. Today we're going to build on top of that and take the next step in the modeling process. So by the end of this lesson, you'll understand what target and predictor variables are, how to normalize your data, how to split your data into training and testing sets, and how to train your logistic regression model to start making predictions. Okay, so let's talk about target and predictor variables. These are the foundation of any machine learning or data analysis project. The target variable is what we're trying to predict or explain. So it's kind of like the answer in our data set. For example, if we're working with customer data and trying to predict whether or not a customer will make a purchase, our target variable might be something like buy with possible answers of yes or no. And then we have predictor variables where these are all the other columns or pieces of information we use to make that prediction. So in simpler terms, the target is what we want to find out, and the predictors are the clues or evidence we use to figure it out. It's important that we understand the difference between these two because almost every step in data science depends on knowing which columns are predictors and which one is the target. Let's look at how we define our target and predictor variables in the breast cancer dataset. So the target variable is the outcome that we're trying to predict. In this case, it's the diagnosis column. This column tells us whether the diagnosis is malignant or benign. The predictor variables would be all the other columns in the dataset, things like mean radius, texture, and smoothness. These are the features that help the model learn patterns and make predictions about the diagnosis. So when we prepare our data for modeling, we usually separate these into two variables. We have our y variable, which holds our target, and our x variable, which holds our predictors. So in this code snippet, we're basically telling Python to do two things. Take the diagnosis column and store it in y, which will represent our target. And then for our x, we want to keep everything besides the diagnosis column for our predictor variables. And you'll notice that in this line, we don't include in place equals true because in place equals true would change the data set entirely, but we only want to change it for this x variable. So because of that, we leave in place out. You can also think of your target variable as the dependent variable, while your predictors are the independent variables. And they're also referred to as features and labels in machine learning specifically. But all of these terms mean the same thing. The target is what you're trying to predict, and the predictors are the information you use to make that prediction. Now let's talk about normalizing your data, which is one of the steps that we need to take before we can start training a model. Normalization means adjusting the values of all your predictor variables so that they're on a similar scale. The goal is to make sure that no single feature dominates the model just because it uses larger numbers. So here's an example from the breast cancer dataset. This is before normalization, and as you can see, we have features like the texture mean and smoothness mean that are small decimal values, but we also have features like area mean that go into the hundreds or even thousands. So the problem with this is that machine learning algorithms, especially models like logistic regression, are sensitive to scale of input values. if we don't normalize this data, our model might pay more attention to area mean just because it has values that are much larger, even though smoothness mean and compactness mean are all just as important for predicting whether a tumor is malignant or benign. So, by normalizing the data, we're basically telling the model to treat every feature equally and to focus on the patterns, not just the size of the numbers. Now that we understand why normalization is important, let's look at how we actually do it using scikit-learn's standard scaler. Standard scaler is one of the most common tools for standardizing data. What it does is pretty simple. So for each column in your dataset, it calculates the mean and standard deviation, and then for every single value, it subtracts the mean and divides by the standard deviation. This process rescales your data so that the average value becomes 0 and the spread of the data becomes 1. So let's look at the example that I have here. Say we have a feature age with the values 20, 40, 60, and 80. The mean of these numbers is 50 and the standard deviation is around 25. So after using the standard scaler, the numbers become negative 1.2, negative 0.4, 0.4, and 1.2. What this means is that now all the values are centered around 0 and scaled according to how far they are from the mean. The value 20 is 1.2 standard deviations below the mean, and 80 is 1.2 above it. So by doing this, every feature in your dataset, regardless of its original scale, becomes comparable. In short, standard scaler helps your model focus on the patterns in your data, not just the size of the numbers. So obviously, we don't really need to understand all the math behind how this tool works. I just thought it might help you understand what exactly is happening and how we get to these normalized numbers. But the important thing is your numbers are all on the same scale so that your model can learn correctly from your data. So this is what your code would look like. In the first line, we're importing the standard scaler tool from scikit-learn's pre-processing module. And then in the second line, we're creating an instance of the standard scaler class and storing it in a variable called scaler. You can think of this as setting up the tool. It hasn't done anything yet, but it's ready to be applied to our data set. And then in the third line, we have the fit_transform method, which does two things. It calculates the mean and standard deviation for each column in X, and then it uses those values to scale the data. So after this step, all of your predictor variables and X are now standardized, so they're centered around 0 and have a consistent scale. And then in the last line, I'm just calling the variables so that we can see what X scaled looks like. And you can see that it looks a little messy. There's a lot of decimals, positive and negative values, but that is exactly what we want. Each number now represents how far that original value was from the mean, measured in units of standard deviation. And now our data is all set for doing logistic regression. So the next thing that we want to do is splitting our data, and we usually divide our data set into two main parts, a training set and a testing set. The training set is the portion of data the model learns from. So during training, the model looks for patterns and relationships between the predictors and the target variable. The testing set, on the other hand, is data the model has never seen before. So after training, we use this part to see how well the model performs on completely new examples. This step is extremely important because if we train and test on the same data, the model can end up just memorizing the answers instead of truly learning how to generalize. And this is what we call overfitting. So, by splitting the data, we can make sure that our model is being evaluated fairly, just like how we test students with new questions instead of the ones that they practiced. So, splitting our data helps us understand whether our model can handle real world data, not just the examples that it was trained on. So, this is what the code would look like, and the first line of code, we're importing the function that we'll use to split our data, again from scikit-learn's. The train test split function is from scikit-learn's model selection module, and this will just help us split our data. The next line, we have all these different variables, and we're splitting it using the train test split. So what's happening is that x scaled is representing all of our predictor variables or features, and y is representing our target variable. And then we have a test size of 30% or 0.3, which means that 30% of our data will be used for testing, and then 70% will be used for training. And then we have a random state of 42. This just makes sure that the split is the same every time you run your code, and it helps keep your results consistent. And you can literally use any number, it doesn't matter here. And then once this is run, you'll have 4 separate data sets. You'll have your X train and your Y train, which is used to train the model, and then your X test and your Y test, which is used to test how well the model performs on new unseen data. And again, this step is important because we want to see whether our model can perform well on data that it hasn't seen before. And without splitting, we might only be testing how well the model memorizes the training examples instead of how well it actually learned the underlying patterns. So now that we've split our data, the next step is to train the model. When we talk about training a model, we're really talking about teaching it to recognize patterns in the data. So in this case, it would be patterns that help predict whether a tumor is malignant or benign. We use the training set to do this, so the model looks at all the predictor variables like the mean, radius, texture, and smoothness, and tries to figure out how those features relate to the target variable, which is the diagnosis. In logistic regression, this means finding the best coefficients or weights for each feature. These weights determine how much influence each variable has on the final prediction. So once the model has been trained, meaning it's learned those relationships, we can use it to make predictions. That's where the testing set comes in. The testing set is a completely separate portion of data that the model has never seen before. By using it, we can evaluate how well the model performs on brand new data. So this step is what separates a good model from an overfit one. A well-trained model doesn't just memorize the data, but it learns the actual pattern so that it can be applied to new situations. So to actually start training our model, we're going to be using the logistic regression model from scikit-learn's linear model module. So this model will be using the sigmoid function that we learned about earlier to estimate the probabilities between the two classes. The next line, we have LR equals logistic regression. So we're creating an instance of the model and storing it in the variable LR. You can think of this as just creating an empty model. It hasn't learned anything yet, but it exists. And then next we have LR.fit xtrain ytrain. So this is a step where we actually train the model. The .fit function tells the model to look at the training data and the correct labels, or it tells us to look at the training data, which is xtrain, and the correct labels ytrain to learn the relationships between them. Logistic regression does this by finding the best coefficients or weights for each predictor variables, and these coefficients determine how much influence each feature has on whether a tumor is malignant or benign. And then we have ypred equals lr.predict xtest. So now that the model has been trained, we can use .predict to test it out on new unseen data using our test set, which is xtest. The output contains the model's predictions for each sample in the test data. So overall, we use .fit to learn and .predict to test. Finally, we want to evaluate how well our model performed. So to do this, we can use scikit-learn's accuracy score function, which measures the percentage of predictions the model got right. So in the first line, we're importing the function that we will use to calculate the model's accuracy. And then in the next line, we're seeing how the function compares the true labels from our test set, which is ytest, to the predicted labels from our model, which is ypredicted. Behind the scenes, it's using the formula accuracy equals number of correct predictions divided by total predictions. And then finally, we can print the accuracy so that we can evaluate how well the model performed on unseen data. So in this case, we had a 98% accuracy, which means that it correctly predicted whether a tumor was malignant or benign 98% of the times. And this is a really strong result, and it shows that our model is performing very well on new and unseen data. If your accuracy score isn't in the 90s or the 80s, I wouldn't worry about it. That is completely normal. And in our next lesson, we're going to be talking about hyperparameter tuning, which will help us adjust the model's internal settings so that we can improve its performance. We'll also be talking about new evaluation metrics like the confusion matrix, precision, and recall. And these metrics will help us go beyond accuracy and really understand how our model is making its predictions and whether it's missing any important cases or making false alarms. So that was all for today, and I will jump right into doing a little walkthrough with the breast cancer data set. Alright, so this is where we left off in TD1. So to continue that, we want to first split our data into the target and predictor variables. So for our target, we can just do y equals data diagnosis. And then for our predictors, we can do x equals data dot drop diagnosis and then axis equals 1. We don't use in place equals true for this because we don't want to change the entire data set. We only want it to be for X specifically. So then now we have our target and predictor variables. Alright, so then after this we want to normalize our data. So to do that, we're going to import the standard scalar from scikit-learn. And then we're just going to make an empty variable. And then we can actually scale our predictor variables. And then just to see the results from this, we can just call it, what did I do? Alright. So everything is now normalized, as you can see. And it all looks good so far. So we can continue and split our data into training and testing. So to do that, we're going to import the train test split from scikit-learn. And then we can do X train, X test, Y train, and Y test. And then again, your test size could also be, like, you could do 20. I think 30 is like a good split. And then your random state also can be literally any number as long as it's like positive, I think. And then after we split our data, we can actually train the model. So we can import the logistic regression model from scikit-learn. And then this is just creating like an empty model. And then we can do dot fit and put our training data in there, and then we can do our prediction equals our test. And then we can just double check by running y prediction, and we can see that it's all zeros and ones, which is exactly what we want, because 0 and 1 stands for malignant or benign in the diagnosis column. And then again, if we do like y test, it's all zeros and ones. So everything is looking good. And then finally, we can just see our accuracy score. And finally, we can print our accuracy score, and then you can see that this is the result.